Hello, so my name is Acton. I run LUNAnomics, which is a organization attempting to advance lunar exploration on the moon. And I'm speaking with Tim here. Would you like to introduce yourself?
Hi, my name is Tim Broslav. I'm a recent PhD graduate from the Space Resources Program at the Colorado School of Mines, and I recently finished up my PhD, of course, on a topic that's very dear to me, on asteroid mining technology. And on this topic, I studied asteroid mining technology called optical mining. It's a technology that was invented by Transastra. It's an asteroid mining company out of California, and of course, I can go a bit more into that once I start presenting. Let me actually share this presentation. I confirm, are you seeing it on your end?
Yep, I see you.
Perfect. Okay, so let's learn about harnessing the power of light to mine the solar system. First, I'll go a bit into the introduction about the topic and some background information. I'll delve into some of the simulant work that went into this work, as well as the test equipment, the model that was made from this research, and finally concluding with results and insights. So optical mining is a technology for asteroid mining that uses focused light instead of contacting methods, and it's being developed by Transastra to harvest water from 1 to 10 meter carbonaceous chondrite asteroids for ISRU development, or in situ resource utilization in space. For instance, you can provide water that can be used to make propellant or consumables in space without having to use rockets to ferry that material into space. This method utilizes thermal spalling to break away materials from the surfaces of asteroids and concurrently heat them to release volatiles like water. And an optical mining spacecraft would capture such an asteroid, as you can see on the right, with an asteroid containment bag, and inflatable reflectors are then used to focus down the light and drive it onto the asteroid surface. Then cold traps are used to collect volatiles. This is an improvement over excavation of using physical methods, just because you're not dealing with the difficulty of mining in a microgravity environment that would be occurring on these asteroids. And it's also an improvement over physical heating, because you're actually heating small chunks instead of trying to heat an entire large rock. My work entailed a variety of objectives. So given a set of material and beam properties, can you predict excavation rates or response modes of a body undergoing optical mining? For instance, is it going to melt, or will it actually be mined? In this case, will it be spallable? Now, also looking into which conditions optimize volatile yield and excavation rates. And furthermore, can this method be successfully applied to asteroids in space? So a little bit of background information about thermal spalling. It's defined as a production of very small fragments or spalls from a material surface. And this is generally studied in terrestrial rocks, concrete, and ceramics here on Earth, and it occurs from thermal stresses. It's actually a subtype of a failure process that can occur once you input a heat onto a material, causing it to thermally stress. Here in the bottom right, you see a compressive zone and a tensile zone that forms when a material is heated from the top down. Now, thermal spalling occurs when failure happens in this compressive zone. Other failures may also occur. For instance, in a tension zone, you can have just a huge fracture that would happen. And this is not very conducive to thermal spalling operations. On the left, you can see thermal spalling of an asteroid simulant. That was basically a recording of some of the experiments that I conducted. Now, thermal spalling that this optical mining technology is based on can be described in a few simple steps. At least this is the generally accepted view of it. Considering the compressive stress zone shown earlier, you have heat penetrating the material, and the material in that zone would undergo thermal compressive stress. As it flows, and this is before entering the tensile zone, you encounter a critical flaw within the material that is much weaker than the surrounding material. This forms a nucleus point for fracture propagation. This fracture would actually spread parallel to the stress field, so parallel to the surface layer, causing eventually it'll spread far long enough to create a critical length and cause the material to start buckling and eventually to violently erupt forward as a spall. So thermal spallation is actually not, I would say, very novel. It's been used at least since the 60s, but it's been known for quite a period longer before that. It's been long used by ancient people in mining. It's been known to have very great penetration in hard granitic rocks and dense sandstones for like borehole mining and oil exploration. Now, there's a variety of mining parameters that have also been developed. This includes prediction of surface temperatures at spallation, penetration rates, and spall thicknesses. People that have investigated it, like Kolodko and L'Oreal, have noted that other thermal failure mechanisms do show up when you're trying to thermally spall. So this is very important to understand the process. And also, there's a variety of thermomechanical properties that affect this process. So it's not tied to one material property to be able to predict whether or not you can spall a material. Usually, a very complex 3D thermal stress models are used, where you first solve the temperature field within the material based on your boundary conditions, and then you solve for your thermal stresses. This can get quite complex and tedious. However, simpler models have been developed using one-dimensional temperature solutions to the heat equation, as well as using just simple thermal compressive stresses, such as shown in equation 3. Now, to forego modeling complex grain-grain interactions for fracture propagation, some researchers have used the Weibull statistical failure method to model failure due to thermal spallation. And basically what it does is, this is a statistical equation that predicts the probability of a given material volume of material. What's the probability it will spall under a certain stress value. Now, prior to conducting experiments, we first had to develop, I would say, a simulant to work with. Not only did this simulant have to be able to mimic characteristics that we're looking for in asteroids, specifically, we were looking to mimic the chemical composition, but it also had to be a material that we could characterize so we could obtain its properties and use it as inputs into the model that I was making. And so Nectar was developed as a compositional CI and CM subtype asteroid, specifically to mimic hydrated water content 8.5 to 9% by mass. We created hollow cakes, seen on the top, for optical mining tests. We also created cores out of these to use to obtain thermomechanical properties as well as statistical properties. Now, there's some caveats to this work, or this portion of the work. First of all, due to sourcing of new minerals for later simulant creation, new Nectar simulants begin melting under the same beam or radiance conditions that we were using in this test. And so it split them between Nectar A and Nectar B. Furthermore, testing has shown that higher fidelity simulants are vital for future optical mining research. And care should be taken to not only do chemical composition, but also mechanical and surface conditions of what you would encounter on asteroids. This was not done in this work just because of the allotted amount of time that would have been required to produce such simulants. However, it is a very great simulant of composition. Now, to go over test equipment, there's a lot of equipment used during the experiments conducted on optical mining research. However, the three main components are the test bed, the lamp and reflector shroud, and the Apollo vacuum chamber, or in this case, a dirty thermal vacuum chamber. Beginning with the test frame, so it was constructed out of 80-20 aluminum framing. It utilized 3 stages. 2 of those were linear Y stages, and 1 was rotary. This was to position the asteroid simulant cake that we used within the chamber, to position at I would say, at a position of irradiance that we were looking for, because as the light propagated into the chamber, its irradiance did vary up to the focal point and then beyond the focal point. So we positioned this cake at various beam radiances just to see how the mining and volatile production rates were affected. A fiberglass blanket was used alongside aluminum pan to collect small fragments. Load cells were used to record cake mass change, instantaneous cake mass change during operations. There was an aluminum shield that was used to block diffuse light, and a beam dump at the back of the chamber was used to basically ensure that no light was impinging on the back of the chamber that would cause it to heat up, as well as block any of the light from reaching the cold traps that we used. Now, the lamp and reflector shroud housed the superior quartz 15 kilowatt xenon bulb and a 16-inch parabolic reflector. This was used to mimic concentrated solar light in space. These are both water-cooled, and distilled water was used for the lamp and igniter equipment, while chilled building water was used for the reflector. This is all contained within the steel shroud, which was 1/8 inch thick, included with black enamel paint. It also contained venting to vent produced ozone from the bulb, and it included a photography curtain as an extra measure of safety. The vacuum chamber housed a variety of equipment as well. The dirty thermal vacuum chamber, which we called the Apollo, was used in the pressure range of around 30 to 3,000 millitorr to conduct these optical mining tests. Instead of using the door that came with this chamber, we had to create or build a custom 1-inch thick aluminum door with a 13-inch fused silica window and a 6-inch sacrificial glass to allow the light from the reflector and bulb to shine through. It also contained a water-cooled shutter to block light when we needed to evacuate built-up pressure. It also had a carbon dioxide purge gas system to prevent organic deposition on the window surfaces. I'll explain that in a little bit. Liquid nitrogen cold traps were housed in the back of the chamber. I mentioned those a little bit earlier. More so, a residual gas analyzer, RGA 200, was used to detect volatile species, mainly water, during testing. Lastly, 2 cameras were used. One was inside of the chamber to obtain video feed of the test, and one was outside, positioned right underneath the reflector, just to assess, make sure that things were operating nominally during testing. Other vacuum equipment and test equipment includes the aluminum door assembly, the shutters that I talked about, as well as the sacrificial glass to block any, I would say, debris from hitting the main 13-inch fused silica glass, and the liquid nitrogen cold trap coils. So the model that was a big portion of this work was developed based on the experimental results from the test setup that I described. This excavation model was developed as a volumetric finite difference model and utilized Weibull statistical failure to predict excavation rates and response modes of a body undergoing optical mining excavation. So this was developed in MATLAB, used temperature-dependent material properties, included a variety of dehydroxylation reactions, as well as stress relief mechanisms due to surface roughness, the brittle to ductile transition and melt, in order to align better with experimental results. Included a distributive radiative heat flux as the boundary condition, just because the beam that we were working with, it wasn't just a beam of a single irradiance. It had like zones, like a concentric circle, think of it like that. And so I had to make sure to incorporate that in the model. Furthermore, morphological effects like vermicular exfoliation were also included and their effects on the stress distribution. So this model forgoes complex grain-to-grain scale modeling due to its inclusion of Weibull statistical failure. It assumes instantaneous spallation, and it was, like I said, verified from experimental results. The main outputs of this model were spall size, the time to spallation, spall surface temperature, the melt percentage of the surface, and the excavation rate in kilograms per hour. First, after the initial setup of conditions and material properties, the temperature solution was solved at each time step, and this is using the Euler's method. It's a finite difference method with some slight adjustments to include for chemical reactions. The top is the equation that were solved for the bulk nodes, so within the material. The middle equation is what was used to solve at the surface boundary that was impinged by the light beam. And lastly, there was a constant temperature condition for the innermost node. It is assumed that within the spallation time, the heat did not penetrate that far into the material. It was sufficiently far away to basically be infinitely far. Now, as I said, this model incorporated irradiance distributions because the beam of light that we were working with was not constant in radiance. In order to incorporate into the model, these heat equations that I just showed earlier were each solved incrementally for a certain area of the beam that fell under a certain irradiance range. So first we solved with the lower irradiance range. Let's say this is like 20 millimeters square or something. That would fall into the 200 watts per square centimeter. This is used as a boundary condition. Next, this is also solved for the more intense beam, and so on. And so this would have left an array, a multi-dimensional array based on the irradiance level. And so you would have had to combine all of these thermal stress calculations that would result from this multidimensional temperature calculation and the Weibull statistical calculation. And I will go into that in a little bit. So once the thermal field was solved, the thermal compressive stresses were also solved, and it was assumed that these dominated. And so the out-of-plane equation, shown in equation 8, was used to solve for them. Like I said, it was performed for each node at each irradiance bin. In this case, this is like a bin. And this is done per time step. And so you have a 2D stress profile based on the irradiance bins. Like I said, stress relief mechanisms were used to modify the stress value, or modify the thermal expansion coefficient to lower the stress as needed. For instance, if material began to melt, or there was some sort of stress relief going on. Now, the Weibull function that we used to add, to simplify the fracture propagation modeling, we had to sum it up in essence due to the fact that we had a two-dimensional stress, thermal stress array. So thermal stresses were summed up one node at a time for each irradiance bin, and you would add further nodes until the probability of 50% was reached. So let's say the surface node was solved for each irradiance bin, and then the subsurface node was solved if 50% probability wasn't reached for each irradiance bin, and so on. And the model was stopped once a probability of 50% was reached. So just to give you a quick overview of the algorithm, you would have the input variables and mesh properties read in. Then you'd have your setup of the mesh and initialization of conditions. Then, depending on if you're modeling for nectar A and nectar B, due to the fact that these were nectar A had vermiculite exfoliation going on, nectar B did not, that's what caused one of the main differences in the results. So you have either nectar A and nectar B being modeled, starting with the transient temperature and stress calculations for each node. And then stop conditions were checked depending on if significant melting had occurred or if a significant amount of material has been heated. And then the calculation was either redone or this was stopped, and certain variables were calculated and stored as outputs. And these are the ones that I showed in the table earlier. So initial excavation rates predicted by the model actually exceeded the rates determined from the experiments. And so this was thought to result from potential variations in the input properties due to errors in either their measured or their assumed values. Now, it was assumed that these variables varied within certain ranges, and so they were varied within the model to see how they affected the results. Now, variables with the largest impact on the model predictions were selected based on sensitivity analysis. We couldn't really vary every single variable. That was too time consuming. And excavation rates, which resulted in a decrease near focus from the sensitivity and tuning effort, were selected for showcasing the results in the model. Now here are all the results, both experimental and model. So one of the biggest challenges of this experiment, working with a carbonaceous simulant, is you're dealing with large organics that are heated, and they can deposit on surfaces within your vacuum chamber. And that's what occurred for the sacrificial glass you see here. We initially developed a carbon dioxide purge gas system to clean it. It did work. However, it did make things a lot more complicated, specifically for the test setup. And so we decided not to use it for further experiments. It also, I would say, added extra water, because this wasn't 100% pure CO2. It did have some leftover water, or either that or the line was leaky, but it added water into the test system, which basically led to incorrect results for some of the early tests for water production rates. Here, seen here are the simulant cakes from Nectar A and Nectar B at the same irradiance. You can see, of course, Nectar B melted significantly, and this is because it did not have what's called unheated vermiculite. So vermiculite was one of these minerals used in making the simulant. For a later simulant for Nectar B, we accidentally purchased vermiculite that was already preheated, so it didn't really undergo this huge expansion step once heated, because it already happened to it. Now, that was a big driver of stress within the material, causing Nectar A to explosively spall under the light. And this didn't happen for Nectar B because you didn't have this large stress rise. So that was one of the main reasons why it didn't really it wasn't really able to be optically mined. Now, regarding excavation rates, you would have a max and sort of average rate. The max was obtained from an instantaneous load cell readings that were averaged over 1 minute. The average values were obtained from just using the mass of the Nectar simulant before and after, dividing by the time of light on the sample. Of course, the instantaneous rates are higher because they weren't really constant, because there's a lot of things happening to I would say mess up with the excavation rate, like the coating on the glass, for instance. But between Nectar A and Nectar B, you can notice a significant difference in excavation rate. Nectar A had approximately 4 to 5 times higher lower rate. Both, however, show an increase as you go up in irradiance. and then a sudden decrease as you go to higher radiances. And this is thought of as more of an increase in the melt formations, as well as softening of the material as it gets hotter, because you have a much higher irradiance beam heating it. Now, for water production rates, these were estimated using the residual gas analyzer. The nectar A on the left has a positive correlation against the average irradiance of the beam. Nectar B does not. It sort of seems stagnant compared versus the actual irradiance of the beam. Also has a much lower water production rate than nectar A. Now, this is tied actually to the surface refresh rate. So basically, the water production rate was tied to the excavation rate, because as you have more material being excavated, you have more of it being refreshed. So you have the dry material is gone. You have less dry material that can evaporate water, or I wouldn't say evaporate, dehydroxylate the water from the minerals and so on. So you have this refresh going on. This was not happening for nectar B. You just have a melt zone that once desiccated, you'd have really low to no water production. Shown here is a follow-up testing using a TGA-MS test setup to showcase the differences between unspalled and spalled samples of nectar A and nectar B. Nectar both actually showcase that they lost water around the 400-degree mark, and this is due to some talc dehydroxylation, so talc lost water. So both showcase that they actually did produce water from this mining method. This also showcases the actual water pressure fraction, in this case, water volume fraction, which you can basically mean the same thing, showcasing that unspalled samples of nectar A and nectar B did have significant water fraction in the 400-degree range, while spalled samples did not, showcasing that they did lose the majority of their water, both nectar A and nectar B samples. Though, notice nectar B, there is certain areas of nectar B, the periphery of their melt zone. So their melt zone and on the periphery was what I would call like centered, a little bit of a centered area. It still did contain a non-negligible amounts of water. So this also showcases that only a small portion of nectar B really lost a lot of water, and that was the portion that was melted. Now this is the volatile loss efficiency for nectar A and nectar B. Basically, did it lose all the volatiles that it could out of the mining? Nectar. Now, I would say nectar A. This also contains water loss efficiency on the right, and volatile loss efficiency on the left. Nectar A has low water efficiency, so it has low volatile efficiency compared to nectar B, obviously because it did not get as hot before spalling, and also because most of the volatile mass loss wasn't just water, it was also carbon dioxide and some sulfur compounds. However, compared to the water loss efficiency, so did it lose all the water that it can? It was basically on par with nectar B that got to a much hotter surface temperature than nectar A. Once again, though they had the same water loss efficiency, nectar A did produce more water. This is tied to the fact that its surface was constantly being refreshed. Now, regarding the model predictions, so for the excavation rate, the model overpredicted rates for nectar A. However, on a qualitative note, it did predict a rise and a drop off in excavation rate as you neared higher irradiances for nectar A, which meaning it can successfully be used to optimize your mining based on your beam parameters. The model also predicted no spallation at all conditions for Nectar B. Now, Nectar B's mass loss was so low, I would say, qualitatively speaking, it did really predict that there was no thermal spalling occurred, because it was very negligible. It was very small spallation occurring under Nectar B, since most of it was melted. Furthermore, the model predicted the surface temperatures at spallation. These ranges, by the way, are due to the sensitivity analysis that was done. The tuning and sensitivity, the tuning and varying of the input thermomechanical variables. For all conditions for Nectar B, the model predicted melting would occur, which was in alignment. And I should say this is the maximum surface temperature that. There was a range of temperatures. This is just the maximum. And for the Nectar A, the model did predict that there was going to be some areas that would exceed the melting point of the material, though this was not happen until around 400. It's around 400 to 450 watts per square centimeter, which aligns with the drop-off of the Nectar A mining rate. Now, regarding the actual surface area of the melt, the model predicted somewhere in the range of up to 2.5% of the entire beam surface would cause melting, all the way up to at focus for Nectar A, meaning it's very, very small melt percentage, which aligns very well with what was observed. For Nectar B, it predicted a minimum of 20%. This is because there was a stop condition in the model that basically it stopped running once melt exceeded 20%, based on a literature review of how melt affects stresses in rocks, and around 20%, you'd see a significant reduction in thermal stresses, and so this was used. However, so it's basically a minimum baseline, because I did measure the melt areas for Nectar B, and all of them are above 20% at least. So this definitely correlates well with what was observed. So, concluding insights. Optical mining has been shown to excavate and produce water from compositional asteroid simulants at 1 meter scales. It builds on the testing that was done by Dreyer et al. In 2016. And it's the first work of its kind that presents both an experimental and numerical study on how to mine an asteroid. That's a one-dimensional finite difference model has been developed that shows excavation rate trends, and response modes with adequate accuracy, though they require tuning. And it can be used to predict response modes and excavation rates from known bodies, as well as how to optimize for excavation rates. Water production has been directly tied to excavation rates from surface refresh. Also, there was things learned about how to optimize this process. It requires something on a radiance range that will give a surface temperature rise just below the brittle ductile transition zone of the material, as long as the water release from the minerals occurs well below this temperature threshold. Now, also has been shown that mineral morphology greatly affects fallibility of weak materials. This has been shown due to the inclusion of the vermiculite mineral in both Nectar A and Nectar B, where in B it was already exfoliated, and Nectar A was not, and it led to a very large conducive spallation in Nectar A. Furthermore, automated irradiance control is vital to excavation operations, as has been shown in how very, very high irradiance can significantly decrease your excavation rates. And so you must be able to normally have your beam irradiance at one level, at your optimal irradiance level. Next, a variety of stress relief mechanisms have been shown by the excavation model to explain the decrease in excavation rates at high irradiances, and these were the surface relief conditions, the brittle to ductile transition, and the melt formations that I included in the model. And so what does this data suggest about space applications? Well, for successful optical mining excavation operations on asteroid bodies with that are regolith strewn, the regolith must be hydrated and homogeneous and uncompressed. And to leave it off, the possible topics for future work, there's a variety of them. One is the effects of desiccated layers in asteroid surfaces on optical mining. So this has been proven. Well, one example of this is, I believe it was on Hayabusa 2. They were looking at the surface of the asteroid, but they couldn't really ascertain whether or not it was a C-type because the surface layers were weathered so much that they had lost their hydrated water content. And so this may occur for some asteroid bodies and should be investigated. Next, in fact, how does microgravity, electrostatic surface charging, and dusty environment affect the optical mining excavation process? Use of higher fidelity asteroid simulants in optical mining is also recommended, as well as testing with a variety of hydration states within the actual simulant. So we tested with 8.5 to 9%. But what if you did 15% by mass, or something like 4 or 5%? Will the method still work? Lastly is the prevention of organic vapor deposits on optical surfaces. So your vapor deposition of organics has a huge effect on your ability to mine, because you're basically going to end up blocking your light, prevent it from reaching your asteroid surface. And with that, I'll leave it to questions from you, Zach. Once again, thank you for letting me present about my work.
Yeah, Tim, that was fantastic. I've heard of this concept before, but I've never had such a thorough explanation of the principles behind it. So thank you so much.
Yeah.
Yeah, I had a few questions. I guess my first one is, what is the output quality of the water that is produced from the optical mining process? Like, how is it captured and separated, and then what's its overall purity when it's released?
Yeah, so it would have to be purified because it does contain a lot of sulfur compounds. There might be some metals in there. So I didn't really test the water that I was working with. I was getting such low amounts. The method that I used to basically weigh the water, so I collect it in little chem wipes. I'd put it into these containers, and then I'd bake the water out. Well, first I'd take the mass of everything, and then I'd bake the water out, just because there's such a low amount of water, to try to ascertain how much water I obtained from a test, and it was a very rough estimate. And there was a low amount of water also because we had to run these tests quick, due to the organic vapor blockage issue. But going back to your question, it's not pure water. It will have to be separated from some of the other compounds.
Okay. And to follow on that train of thought, like envisioning this as operating in space in a vacuum, microgravity, what is the operating temperature like within the vacuum? Like, I guess the main question is, that water is going to exist in a liquid state, and how is that going to be handled?
So ideally, you'd want it as a vapor. So that's one of the reasons why I ran operations at all the way up to 3,000 millitorr or 3 torr, because around 4 point something torr or so, you're going to have the triple point of water. Beyond that, liquid water can exist. Below that, you don't really have liquid water. It makes it easier to capture, and you're not really affecting, you're not really depositing water elsewhere in this, like from absorption, for instance. And temperature-wise, it all really depends on the dehydroxylation temperature of your minerals. But I would say, roughly speaking, it'd be somewhere between 300 to 600 Celsius. Probably closer to the lower end. Just because around 600, you're going to have most materials are going to start getting soft. You're going to like your material properties, your Young's modulus decreases, so your stress buildup actually goes down, and you make it harder to spall.
And the spacecraft that you showed on one of your earlier slides, is that the Honeybee spacecraft that does the optical mining? Is that what it's called?
So this is a prototype spacecraft. Here, I shouldn't have exited out of the presentation. So this is a prototype spacecraft that they have publicly released. I can't comment on what the current state of this is, but this is what's been publicly released. And this is not there's going to be other spacecraft beyond this one. I think this is just a scaled down version.
Okay. And so I guess the general workflow is that another spacecraft properly identifies a suitable, I guess, boulder-sized asteroid fragment. Is that correct?
Yeah, that would be the case. Yeah.
Okay. And then it brings it to this spacecraft, and this is what's conducting the optical mining process.
No. So once a target has been identified and selected for optical mining operations, this spacecraft would actually go there and mine it.
Okay.
And it would one of the cool efficiencies about this is it's going to try to reuse the water or some of the water that it collects as propellant.
Okay.
Yeah.
That makes a lot of sense. Is that what is that process or that propulsion system?
Solar, like a thermal rocket, sort of. Solar thermal rocket engine.
Right. So it's additionally using its ability to collect like optical light as part of its propulsion system as well.
Yeah.
Yeah, that makes a lot of sense. How does I guess, if the optical mining process, I imagine, at optimal efficiency is running for hours or hours and hours at a time. How's that affected if it's I guess it's found a target asteroid to mine? Is it going to stay in that location, or is it going to maneuver away from the asteroid so that way it's an optimum sunlight?
That's a great question. Something I don't think I have the expertise to answer, because I only mainly dealt with the excavation portion of the optical mining method. This would be a question for Joel and company. Now, I would say yes, orbit does have an effect, because the further away you get from the sun, the lower radiance. So that might have an effect. It would definitely have an effect on the irradiance of the light that you can gather and use, like focus it down. Because here it's what, like 1367 watts per square centimeter or per square meter. That's the radiance of the light that hits like the ground. And depending on the orbit of the asteroid, it'll probably be a near Earth asteroid. The farther you get away, you're going to have to deal with lower irradiances that you have to work with and turn into or focus down into a mineable beam. But that also basically, I'm not sure if that's gonna have a huge effect or not. That's question.
Okay. Yeah, I guess I was focused on the, I don't know, hypothetical, like, rotation of an asteroid where, if you were to find a suitable, boulder to start mining, and if the rotation of the asteroid consistently puts, the vehicle or the spacecraft in periods of darkness, I guess it would make sense to move the vehicle away from its initial location to be in full sun.
Oh, okay. So these are small asteroids. So you're not going to really run into that problem.
Okay.
Yeah, you're not going to really run into a problem of, the shadowing effect.
Okay. I think my other question would be specifically on the research that you did. What are areas of research in optical mining that is extremely difficult to model or test on Earth and would require substantial testing like in microgravity?
Yeah, one of them is microgravity, as you mentioned. I would say the other one is working with a high fidelity simulant. So working with simulants, it's really difficult to have one and all encompassing simulant. You're trying to mimic certain characteristics of the body or whatever you're trying to simulate. So it can either be like grain size distribution, or it can be a strength, chemical composition. It's really difficult to get everything. And so, but another add-on to that is for us, for this work, it also had to be characterizable, because I was making a model, a predictive model. So that's what I would say make it even difficult, because asteroids are very weak, very fragile bodies, and being able to create something that you can characterize and have the properties of an asteroid, like how the surface is structured, your chemical composition, maybe have like some kind of desiccated layer on top due to space weathering. I think that would definitely go a long way in helping this sort of research.
Okay.
Yeah.
Are there any, I guess, final thoughts or that you would like to speak towards?
This is an amazing technological concept, and I think it has great potential. It was awesome working on things like this. This is, like cutting edge. I think it's much more scalable than other methods, than a mechanical mining method, because in reality, you're really scaling your inflatable reflectors and so on. I may be wrong on this, because I'm not really into the spacecraft design, but to me, just by working with the concept, looks much more easily scalable than other mining methods.
And I'm sure you can't speak too much to like the details of upcoming demonstrations, but is Transacid planning on something in the near future, like in this?
I do know they were planning a demonstration concept, though I don't know where they are at with that right now. That would have to be a Joel question.
Oh, sounds good. All right, Tim. Well, thank you so much for presenting your research to us and to the broader space resources community. And thank you for all your hard work on this in this field. We definitely need more people like you working on this for for all of us.
Yeah, and if there's any more questions, I did have to significantly reduce the content of this presentation. So if there's any more questions, especially in the modeling side, feel free to reach out.